Welcome back. In this video, we're going to be going through some conservation of energy problems. So pause the video right now so you can do these problems on your own, and when you're finished, go through them with me and check your solutions. One of the problems goes with this graph, so you're definitely going to need that as well. Alrighty, number one. What is the kinetic energy of a 400 kilogram car moving at 10 meters per second? Kinetic energy equals 1/2 mv squared. In this video, I deliberately gave us all SI units, so we didn't have any unit conversions. So it's just 1/2 400 kilograms, 10 meters per second squared. And when you plug in SI units into an energy equation, you should get joules. So this should just be half of 400 is 200. So 200 and then two more zeros. 20,000 joules should be our kinetic energy here. So pretty straightforward. We're just plugging into 1/2 mv squared. This problem is kind of similar, except instead of kinetic energy, we're doing potential energy due to gravity, which is mgh. Our mass here is 15. Gravity is 9.8. And the height is 10. And again, I used all SI units, kilograms, meters per second squared, meters, and that will get us joules. So plug that into the calculator, and you should get 1,470 joules of potential energy. Number three, now we're kind of putting number one and two together. The total mechanical energy. So mechanical energy should just be kinetic energy plus potential energy. So the kinetic energy, 1/2 mv squared again, and the potential energy, mgh. So we're just plugging and chugging. 1/2, and the mass is 3. The velocity is 15. Mass is still 3. Gravity is 9.8. We're on Earth for all these problems. And the height is 12. So again, some plug and chug. Not going to try to do this in my head. And I'm getting 690.3, and that unit for energy is, of course, joules. Okay, so now we're talking forces. So when we have forces and energy, we're going to be using our equation work equals force times distance. Okay, a force of 300 newtons pushes on a 15 kilogram box, which is initially at rest, and it pushes it for 50 meters. Determine the work done on the box by the force and the final velocity of the box. So fill in the equation. The force is 300 newtons, which is an SI unit, and the distance it pushes it is 50 meters. So we should just get 15 with 3 zeros. So the work is 15,000. Work is energy. So joules. 15,000 joules is the work done on the box by the force. Now the final velocity. Well, what did that work do to the box? It increased the velocity. So all of that work went into increasing the kinetic energy, the 1/2 mv squared. So we can fill in the equation. The mass was 15. Notice how we didn't need the mass here. And v squared. So this is just 7.5 v squared. And we can do a little rearranging and square rooting. So 15,000 divided by 7.5, and then square root it. Raised to the half power. We get v equals 44, and I'll round it to 0.7 meters per second. Okay, not too bad. The trick there was just to set the work equal to the kinetic energy, because the work is just something that changes the energy. So whatever kind of energy this work is changing, that's what we set it equal to. And it just changed the kinetic energy. I didn't mention a hill or anything like that. Okay, so we have a car moving at 30 meters per second, applies the brakes, and it comes to a stop. Determine the force of the brakes on the car. Work equals force times distance. All right, so what kind of work did the brakes do? Well, the brakes slowed down the car, so it decreased the kinetic energy of the car. We can say the kinetic energy is the work, which equals FD. So 1/2 mv squared equals force times distance. Okay. Fill in the equation. 1/2. Mass is 1,500 kilograms. Good SI unit. V squared. 30 squared. And we're looking for the force, so we don't have that. And the distance is 150. So I'm going to divide both sides by 150 after I plug the left side of the equation into my calculator. And I get the force is 4,500 newtons. Now, I'm not concerned about the sign here. I could say it's a negative force since it's slowing it down, but I'm not trying to get nitpicky here. All right. How much work is required to lift a 50 kilogram block to a height of 80 meters? And what is the power required to do so in 50 seconds? So work equals the change in energy, like I've been saying, and raising a block to a certain height is changing the potential energy, mgh. So the change in energy, which is the work, is the mass, 50. Gravity is still 9.8 meters per second squared. And the height is 80. So this is going to be part A. 50 times 9.8 times 80 gives me 39,200 joules of energy, which is my work. Now, what's the power required to do so in 50 seconds? Power is your work over your time, or your change in energy over your time. So that many joules in that many seconds. And I get 784. Don't forget the unit of power in SI is the watt. 784 watts. A 5 kilogram block is placed at the top of a 30 meter tall frictionless hill. So the height of the hill is 30 meters, and then it's going to kind of slide down there. The angle really doesn't matter. When we're doing conservation of energy, all we're dealing with is height. So, and it's released, and then we have a spring at the bottom with a constant of 7,000 newtons per meter. If energy is conserved, find the velocity of the block right before it hits the spring. So if we're starting up here, that's all mgh, potential, and right before it hits the spring, it's all kinetic. So the velocity right before it hits the spring, cross out the m's, and we get, I'll multiply both sides by 2. So v squared should just be 2 times 9.8 times 30, and then we'll square root it to get the velocity, and we can say v equals 24.2 meters per second. So that's our first answer. Now we want to know how much the spring will be compressed when the block comes to rest. So now instead of saying that the mgh is converted into the kinetic energy, I can say that the mgh is converted into spring energy, 1/2 kx squared. Now I could have also said that that kinetic energy right before it hit the spring is converted into the potential energy due to the spring. But I'm not going to do that because I don't want to use a rounded number. And also, if I ended up messing up this answer, it's going to mess me up for the next part. So why not use the numbers that we started with? So mgh, so the mass is 5. We didn't have to use that before because it canceled. 9.8 times our height. And that's going to equal 1/2 k is 7,000. That's SI units times x squared. So to simplify a little bit, we get 1470 equals 3,500 x squared. So divide that by 3,500, the 1470, and then we get 0.42. We need to square root that, and we get the displacement. X is your displacement, 0.65 meters. A ball at the edge of a 30-meter cliff is thrown into the air with a velocity of 15 meters per second. Okay, so I have a cliff. Definitely want to draw a picture here. Is thrown into the air with a velocity of 15 meters per second. The ball rises vertically. Okay, so it's going to go up and then come straight down and falls to the ground below. Determine the final velocity of the ball just before it hits the ground. So conservation of energy says the energy at the beginning equals the energy at the end. I write it as E1 equals E2. You could do EI, like E initial equals EF, E final. Doesn't really matter. But the energy at the beginning, well, I have kinetic energy and I have potential energy. And then my energy at the end, well, it falls off of the cliff, so it's no longer above ground level. So it's just kinetic energy when it hits the ground. To simplify a little bit, I can get rid of all of the M's. Don't forget this V is different than this V. So I'm going to write V1 here and V2 here. All of the M's go away. And now I can just fill everything in. 1/2. And then V1 we said was 15 GH. And the H was 30. That's going to equal 1/2 V squared, V2 squared. So I'm going to plug in the left side of my equation into my calculator. So I get 406.5 equals 1/2 V squared. To get rid of that 1/2, I will double both sides to get 813 equals V squared, and then square root it, and I get V equals 28.5. And that makes sense that my velocity went up since the initial velocity was added onto by the potential energy we lost. All right. We have this graph and it says that the force varies and we want the total work done and the object's final velocity. Now, to get the work from a FD graph, we find the area underneath the curve. Meaning we're going to find the area of this trapezoid and we're going to find the area of this trapezoid. You can do triangle, rectangle, triangle, triangle, rectangle if you want to. Why don't we actually do that? Don't forget, any area beneath the horizontal axis should be negative. So this is a triangle. We'll do 1/2 base times height and get 40. This one, we have a length of 4, a width of 20, so that should be 80. Like I said, I almost forgot. Negative, negative. And then a length of 2, a height of 20. So negative 20 once we divide length times width by 2. And then here we have 1/2 base times height. So that should just be 15. And the length here, well, 30 minus 12 gives us 18. And 18 times 15 gives us 270. So the total work, we just add all these numbers up, all the individual works. So negative 40, negative 80, negative 20. And then we're going to add on that 285 above the x-axis, or the horizontal axis, I should say. And we get 145, and the unit for work is joules. So that's our first answer. And we want the final velocity. Assuming that all of that work was done to increase the velocity of the object, we could say work equals 1/2 mv squared here. So 145 equals 1/2 50 v squared. So 25 there. So 145 divided by 25 is 5.8, and then we square root it. And we get v equals 2.4 meters per second. So not that fast for a good amount of work, just because the object was kind of large. Lastly, a pendulum is made by hanging a 5 kilogram mass on a string that's 10 meters long. So it's a 5 kilogram mass, and this is 10 meters. The pendulum is pulled back until the mass is 5 meters above where it is initially hung. So I can say that now we have our pendulum like this, and it's 5 meters above where it was before. Assuming the string is tight the whole time, find the maximum speed that the mass will attain when it is released. Now, this is a really good conceptual problem. This problem tests you on whether you know where it's going to have the maximum velocity or not. So we are going to start with no kinetic energy at the top when we're just holding it up there. And when we let it go, it's going to increase its velocity until it gets all the way to the bottom there. And the reason that is because it's losing gravitational potential energy and gaining kinetic energy all the way until it's at its low point. When it's at its low point, that's when it has the least amount of gravitational energy and the most kinetic energy. So we can say that the energy at the beginning equals the energy at the end. Now, the energy at the beginning is just potential due to gravity because it's not moving when we're just holding it 5 meters off the ground. Now, this 10 meters actually doesn't really matter, to be honest, because all that matters is the height off of the ground, or the height above the 0 mark, which we'll set right here. So mgh equals, and then we'll say the energy at the end where it has no potential energy is 1/2 mv squared. Okay, mass cancels, so notice how this doesn't matter. And we just have 9.8 times the height off of the ground, which is 5 meters. Again, I'm setting my ground level here. So 9.8 times 5 equals 1/2 v squared, which is our maximum velocity because we're at the low point. You always have your max velocity when you're at the lowest. So 9.8 times 5 gives us 49. Multiply by 2 to get rid of that fraction, and then square root it. The square root of 98 is 9.9-ish meters per second. So hopefully you did well on this little practice quiz here. And hopefully that you learned a few things from the way that I solve problems. There are tons of ways, tons of different explanations for problems like these. I try to make them as simple as possible. So I hope you got something out of this.
Brad does math.